Yeah. Okay, so we are going together. Later join the classes. You want for the classes? Which one?
I'll join you in a few minutes. The class will start in a few minutes.
Okay, sound. Good morning, everybody.
Recording in progress.
So, I hope you can all hear me. For the benefit of doubt, I would like to reiterate because I realize that some people didn't get how we derive the density formula from the general gas law. So I'll just quickly to show that before we go to the business of the day. Just a minute. Yeah. So I decided to break down the formula so that you can see how we got that density formula. You know, the general, the ideal gas equation equals PV equals to nRT. And then we know N, which is the number of moles, is mass over molar mass. So instead of putting N, we can replace it with mass over molar mass and still multiply by RT. If we now make volume the subject of the formula becomes that means we are going to divide that RT by P if we now make V the subject of the formula. So if we divide that, we have the mass over molar mass multiplied by RT divided by P. We can invert that formula to get PM over MRT. That's 1 all over V. And since we know that our density equals mass over volume, it means that M on top of the V, that's why we inverted that V, so that the V can be the denominator to show the formula density equals to mass over volume. So it means that this our 1 all over V, when we multiply it by the small m, then we should get our density. So, and that was what we did in the next step. M multiplied by 1 all over V. There are m common at the numerator and denominator. Those ones cancel out. And then what we now have is PM over RT. So that is how we got that formula. I hope it is clear now.
Hello.
So I hope that is clear. Do we have any further question on that? That is how we got that formula. So in the absence of any question, I will go to the business of day. I think we have done all of this. So we had doing Graham's law of diffusion. So, a great scientist, Graham, scientist, not supposed to share this. Let's share the other one for me. Share what I'm supposed to share. Yeah. So, I mentioned it, and it's a law we are familiar with. We just try to do some derivations and calculations. Dalton's law of partial pressure. It states that the total pressure of a mixture of gases is equal to the sum of the partial pressure of the component gases. Yes, I can see somebody putting up their hand. Do you have any question? I can see somebody somebody raised her hand. I don't know if you have any question before we continue. So if you look at this diagram A, B, and C, in A, we just had 0.6 mole of hydrogen. In B, we had 1.5 mole of helium. And then in C is now a mixture of helium and hydrogen. The pressure exerted by 0.6 mole of helium was 2.9, while that exerted by 1.5 mole of helium was 7.2. So what Dalton is trying to tell us that if we have gases individually in a container like they are, and you now mix them together, that pressure that they were exerting when they were there alone in that container will still be the same pressure they will exert when they are in a mixture with other gases. That is why the P total in the C component that shows us the mixture of hydrogen and helium totals the sum of is equal to the sum of the pressure of hydrogen and that of helium. Now, we already know from our ideal gas equation that PV equals to nRT, because we are now talking about pressure. We'll make pressure the subject of the formula. So if we have pressure equals to nRT over V, and we have, let's say, three components, P1 for gas 1, P2 for gas 2, and then P3 for gas 3, if those three gases are in a mixture. So it means that the pressure of gas 1 will be equal to the number of moles of gas 1 multiplied by RT over volume. And then the pressure of gas 2 will be the number of moles of gas 2 multiplied by RT over V. And then the third gas, P3, will be the number of moles of gas 3 N3 multiplied by RT over V. RT over V is common to all of them. So if we bring that out and factorize, it means that our P1 plus P2 plus P3 will be N1 plus N2 plus N3, all multiplied by RT over V. I hope we are following. And then our P total will now be the number of moles when you add N1 plus N2 plus N3. That will be the N total multiplied by RT over V. And that takes us to another concept, the mole fraction. We can get our pressure, the pressure of the individual gases or the total pressure by using the mole fraction multiplied by the pressure. Now, when we say the mole fraction, what it simply means is that if you have a mixture of gases, like in this case, we are talking about Dalton's law, each of those gas will have its number of moles. So the mole fraction tells us about the number of moles of each component. That is, if you have component A, B, and C, the mole fraction of A will be the number of moles of A divided by total number of moles. The mole fraction of B will be the number of moles of B divided by total number of moles. The mole fraction of C will be the number of moles of C divided by the total number of moles. So that is what this formula is showing us. The mole fraction is given by the formula X. So XA will be number of moles of gas A divided by the total number. Okay. And we already know from the previous slide that our PAV equals to NART. That's the ideal gas, still on the ideal gas equation. Okay. So it means that our P total V will also be the same as N number of moles total multiplied by RT. If we now divide, we are just trying to derive an equation here, which we shall see. If we now divide PAV divided by P tot V, the gas equation as related to A divided by the total number of pressure. So that will give us NART divided by N total RT. Or if we decide to separate it, because RT is now common, we can cancel out RT. PA over PT will now be NA over N total. Or we can make PA the subject of the formula, and then we'll now multiply PT by NA all over N total. Meanwhile, that NA all over N total, if you look above in the slide, is what we call the mole fraction. So we can actually say PA equals to XA mole fraction multiplied by P total. Are we following? Do you have any question before we move ahead? So these are some of the formulas that we'll be using in solving our questions relating to Dalton's law of partial pressure. So the pressure of the pressure of one of the gases will be the mole fraction of that gas multiplied by the total pressure. We are just trying to show us how we got that formula by going through all of this. Okay. So Dalton's law states that P total equals to P1 plus P2. And then for P1, it will be mole fraction of 1 multiplied by P total, which this is just reiterating what we saw earlier in the previous slide. So if we want to get the partial pressure of one of the gases, it's going to be the mole fraction of that gas multiplied by the total pressure exerted by all the gases. So if this is trying to illustrate to us, we have 3 gases and we have 3 different scenarios. You have gas A colored blue, gas B colored, is it wine or purple, and gas C colored like orange. So in each of these container, they will be exerting different pressure. So we could actually calculate the mole fraction in each of them. If you look at the one, you can calculate the mole fraction. It's just like a child's play in this case. You can just count how many. The gas A is the one colored blue. We have 1, 2, 3, 4 of A. And then we have B as 1, 2, 3. And then we have C as 1, 2, 3. So altogether, there are 10 moles. That's what it means. So if we are representing A at each of those dots to be equivalent to a mole. So if we want to calculate the mole fraction of A, it's going to be 1, 2, 3, 4 divided by all the dots added together. That will be 10. That will be 4 over 10 or 2 over 5. So the same thing when we go to 2. The second container, we can add up all the number of moles, assume each dot to be 1 mole. So it means in gas container 2, we have 1, 2, 3. We have 3 moles of gas A. And then when we add up all the other ones, we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. So it means that in this gas container B, mole fraction of A will be 3 over 15. And then you can play around with the third one as well. So this is just trying to show us how we calculate the mole fraction. So here we have an example. You have 3 moles of gas A, 4 moles of gas B, and 5 moles of gas C in a mixture of gases. And the pressure of A is found to be 2.5 atmosphere. What is the total pressure of the sample of gases? So if we recollect, we have the formula PA equals to XA multiplied by P total. So if we know PA as 2.5 and we know XA as 0.25, then we should be able to get the P total. Okay, so XA will be number of moles of A divided by the total number of moles. That's 3 divided by 3 plus 4 plus 5. That gave us 0.25. And then A minute. Okay. So we are giving PA to be 2.5 atmosphere, and we know this formula. PA equals to XA multiplied by P total. So it means P total will be PA divided by XA. That will be 2.5 divided by XA 0.25. So it means the total pressure exerted by these gases will be 10 atmosphere. I hope we are following. We have another example here. (80 grams each of helium, neon, and argon are in a container. The total pressure is 780 millimeter mercury. Find each gas's partial pressure. So we are given 80 grams of helium, 80 grams of neon, and 80 grams of argon. So for each of them, we first of all calculate the number of moles. So 80 grams of helium divided by number of moles we know is what? Mass over molar mass, is it not? So the mass, 80 grams divided by 4 grams of by 4, which is the molar mass of helium, will give us the number of moles of helium. The same 80 grams divided by the molar mass of neon, which is 20, will give us the number of moles of neon. And then 80 grams divided by the molar mass of argon, 40, will give us the total number, will give us the number of moles of argon. So when we divide 80 by 4, we get 20. When we divide 80 by 20, we get 4. And then we divide 80 by 40, we get 2. So it means that the total number of moles of all the gases will be 20 plus 4 plus 2. That will be 26. Now, to now get the partial pressure, so it means that our partial pressure will be the mole fraction divided by, the mole fraction multiplied by the total pressure. So for helium, for instance, the mole fraction will be the number of moles of helium, 20, divided by the total number of moles, 26, multiplied by 780. For neon, it will be 4 divided by 26, multiplied by the total, 780. And for argon, it will be 2 divided by 26, multiplied by the total, 780. So each of them, if you press your calculator, these are the values at the bottom for each of them. You have the helium having the highest partial pressure, followed by neon, and then argon with the least pressure. So that is just trying to tell us the higher the number of moles, the more will be the partial pressure that gas will exert in a mixture. I can see somebody saying, you can't hear me. Am I not audible? Can somebody confirm they can hear what I'm saying? Oh, yes, you can hear me. Okay, thank you very much. Maybe those who can't hear me, maybe their network is not. Okay, thank you very much. I hope you are following. Yeah. You are following the examples we are doing. So we can go to the next. Okay, so this is another example here. A solid hydrocarbon is burnt in air in a closed container, producing a mixture of gases having a total pressure of 3.34 atmosphere. Analysis of the mixture shows it to contain 0.34 gram of water vapor, 0.792 of carbon dioxide, and 0.288 of oxygen, 3.790 gram of nitrogen, and no other gases. Calculate the mole fraction and the partial pressure of carbon dioxide in this mixture. So just like we did in the previous one, to get the mole fraction, we will need to get the number of moles of each of those gases that have been listed. So the total number of moles will be the sum of the individual mole of the gases. So for instance, the first one is water vapor, 0.34. To get the number of moles, you divide by 18. That's why the first one is 0.34 divided by 18. Mass over molar mass. Mass of water, 0.34. Molar mass of water, 18. The next one, 0.792 of carbon dioxide. The mass, 0.792. The molar mass of carbon dioxide, 44. And then the next one, 0.288 gram of oxygen. We divide by the molar mass of oxygen, 32. And then the last one, nitrogen, 3.790 divided by the molar mass of nitrogen, 28. So when you press your calculator and you add up all of these, you get 0.1809. But we are asked to calculate the mole fraction of CO2. So it means the mole fraction of CO2 will be the number of moles of CO2 divided by the total number of moles. So when you press 0.792 divided by 44, you get 0.018. And then the total number of moles, 0.1809. So when we divide that, our value will be 0.0995. That is the mole fraction of carbon dioxide. And then the next question is to find the partial pressure of carbon dioxide in this mixture. We already know from the formula we derived that the partial pressure of a gas component will be the mole fraction of that gas multiplied by the total pressure exerted by the mixture. So already we've calculated the mole fraction of carbon dioxide, 0.0995, and we are given the total number of the total pressure to be 3.34. So when we multiply that, we get 0.332 atmosphere. So I think that is all we have about Dalton's law of partial pressure. The next one we want to look at is Graham's law of diffusion. Graham's law of diffusion states that the rate of effusion of two gases are inversely proportional to the square root of their molar mass, provided the temperature and pressure is kept constant. What do we mean by effusion? Let's first of all write the formula. Let's convert that sentence we have made, or that story we are telling. Let's convert it to a formula. The rate of effusion of gas 1 divided by the rate of effusion of gas 2 is inversely proportional to their molar mass. The formula, molecular weight of the gas 1, gas 2 divided by the molecular weight of gas 1. Okay? And then, what do we mean by effusion? Diffusion, that we are already familiar with. The movement of particles from regions of higher concentration to regions of lower concentration. If you stand at the corner of a room and you spray a bottle of perfume, that is one example I like to use because perfume smells nicely. That's why I like to use that example. You stay at the corner of a room and then you press, you spray a bottle of maybe antiperspirant body spray. At that corner where you are spraying, the concentration will be high. That is where you start to smell it. In a matter of minutes, the other person at the other end of the room will begin to smell that spray because the particles have traveled from where you sprayed it, the region of high concentration, to the other person at the end of the room at a lower concentration. So that is the way gases diffuse. And that rate of diffusion is dependent on the mass of that gases. The mass, gases with low molecular weight will diffuse faster. The rate of diffusion will be very fast. Gases with higher molecular weight, the rate of diffusion will be slower. We can liken it to two people, one that is an athletic, that has an athletic figure, and the other one that is perhaps doesn't do exercise and not fit. And then you ask the two of them to walk from one end of the room to the other. You see that that one that is very fit or athletic will move quite faster than the one that is unfit. So the same thing that happens with these gases, because I don't want to use, apologies to those who have a fat body. I don't want to use the fat body and slim body. That's why I'm using fit, athletic, and unfit. Okay. So what we eventually see is that everybody in the room will be able to perceive that body spray because it has diffused. Okay. Now, what do we mean by effusion? It is the passage of gas under pressure through a tiny opening. And this is an example. If you have the wheel of a car, you have the tire, and then it gets punctured by a nail. What is going to happen? It's going to go flat eventually if care is not taken. What is happening there is that opening, gas is escaping through it. That is effusion. So effusion of gas particles is through an opening. Okay, so that is the difference between diffusion and effusion. So this is just trying to show us how they got this Graham's law formula. If you have two gases at the same temperature, they will have the same kinetic energy. Let's say we have gas 1 at half m1 v1 squared and gas 2 at half m2 v2 squared. Because they have the same kinetic energy, we can equate them. Half m1 v squared, half m1 v1 squared will be half m2 v2 squared. And then the half will cancel each other. And then when we divide both sides by m1 v2 squared, what we are going to get is that some things we cancel out, and then we now have v1 over v2 to be the square root of m2 over m1. So just trying to show us how we got the Graham's law formula. The velocity of effusion is also inversely proportional to the molar mass, because the questions can be tricked in different ways. It can be so that once you understand the basics, no matter how much the question is being twisted, you will be able to solve or maneuver your way around it. So if we are talking about velocity, rate, speed, it will still be inversely proportional to the molar mass. So instead of saying, if you are giving the velocity, for instance, you don't need to cry that, oh, this velocity we are giving, we are not giving the rate, because there is still a kind of a similarity in the formula. But the time it's going to take for the effusion is directly proportional to the molar mass. It means that if you have two gases, one of a lower molecular weight and one of a higher molecular weight, it means that the one of a lower molecular weight will travel faster. It will take a shorter time to reach its destination, while the one of a higher molecular weight will take more time to diffuse. Okay, so that is why in this formula, the time taken is directly proportional to the masses. I hope we are getting it. Don't get confused. If it is the rate or the velocity, it will be inversely proportional to the molar mass, because the lower molecular weight will travel at a faster speed. A faster speed means a shorter time to get to where it is going. That is why time is directly proportional to the molar mass, while the rate is inversely proportional to the molar mass. I hope we are clear. I hope we are following. Now we can take example. Compare the rate of effusion for hydrogen and oxygen gases. That is the question we are taking. We are asked to compare the rate of effusion for hydrogen and oxygen gases. So the rate of effusion of hydrogen divided by the rate of effusion of oxygen will be, don't forget, this one is an inverse relationship because it is rate. The square root of molar mass of oxygen divided by the square root of the molar mass of hydrogen. The molar mass of oxygen is 32. The molar mass of hydrogen is 2. So if we divide 32 divided by 2, that will be square root of 16. And then the square root of 16 is 4. So square root of 16 is 4 divided by the square root of 2 is square root of 1. Okay? So it means that the rate of effusion for hydrogen is 4 times that of oxygen gas. It means hydrogen will travel 4 times faster than oxygen gas. That is simply what this is trying to tell us. 4 to ratio 1. 4 times the rate of hydrogen is that of oxygen. Hydrogen will travel 4 times faster than oxygen. So that is what that is explaining to us. We have another question here. Carbon dioxide travels at 410 meters per second at 25 degrees Celsius. Find the average speed of chlorine at the same temperature. They have been given the speed of carbon dioxide. And that's, we are looking for the speed of chlorine. So the speed of chlorine divided by the speed of carbon dioxide will be the square root of the molar mass of carbon dioxide divided by the square root of the molar mass of chlorine. So we can make the speed of chlorine the subject of the formula. So that means we multiply the speed of carbon dioxide by what we have in the square root. So we are given the speed of carbon dioxide 410, the molar mass of carbon dioxide 44, the molar mass of chlorine 71. So when you get the square root of 44 divided by 71 and you multiply by 410, you get 320 meters per second. I hope it is clear. It's just a simple mathematics. So what this is trying to tell us is that the speed of chlorine will travel at a lower speed than carbon dioxide, and that is obvious from their molecular mass. Carbon dioxide has a molecular mass of 44, while chlorine has a molecular mass of 71. And Grams has told us that their speed is inversely proportional to their molar mass. So it means CO2 that has a molar mass of 44 will travel faster than chlorine that has a molar mass of 71. And then the last question we shall take for the day. At a certain temperature, chlorine gas travels at 582 meters per second, and a noble gas travels at 394 meters per second. What is the noble gas? We write our formula. V1 over V2 equals to M2 over F1. M2 over M1, sorry. So the velocity or the speed of chlorine divided by the speed of the unknown will be the square root of the molar mass of the unknown all over the molar mass of chlorine. You can rearrange the formula as you wish. You can put velocity of the unknown on top. Put the velocity of chlorine down. Just make sure that when you are writing the molar mass, it is an inverse relationship with the velocity or the speed. So what we can do, we can square the velocity side so that the molar mass side, we remove it of that. If you want to remove the square root, you square both sides so that the molar mass side, you remove the square root, and then the velocity side is squared. So if you make the mass of the unknown the subject of the formula, it's going to be the molar mass of chlorine, 38, multiplied by the velocity of chlorine, 582, divided by the velocity of the unknown gas, 394. So when we press our calculator, what we are going to have is 82.9. And that 82.9 is actually krypton. That is the noble gas that has that formula. I mean, that has that molecular weight. I hope we are following. Is it clear to us? The examples we have taken so far. So, do we have any question? Because this is where we are going to stop today. It's already, our time is up and I don't want to keep you so that you can go for your next class. So in this example, we are looking for the formula or the gas that travels at 394 meters per second. So what we did was to calculate the molar mass using our formula V over V of fluorine over V of the unknown equals to the square root of the molecular mass of the unknown divided by square root of the molecular mass of fluorine. So if you put all those values, 582 divided by 394 in square roots equals to the, 582, which is the velocity of fluorine, divided by 394 will be equal to the square root of 38 divided by the square root of the unknown. The square root of unknown divided by 38. 38 is the molecular weight of fluorine. So if we use that formula and we press our calculator, we are going to get 82.9. The question says, what is that gas that has that molecular weight 82.9? So when you go into your periodic table, you will see that you have krypton as that gas with the formula, with the molar weight of about 83 gram per mole. So that is where we'll stop for today. We'll take more examples in the next class. I think we have just one more. So if I can find any other example, I'll bring it to class and then we move to the next topic on deviation from gas law.